Our next speaker is Arno, who's talking about mixed model small sample.
Yeah, thank you. I'm Arno. I'm a freelance statistician, and nowadays big data, AI is all the hype. Particularly, this talk is scheduled in between multi-threading talks, so probably you guys are used to crunching huge amount of data, but my job is to make the most if you only have a small sample, a small data set. In particularly, Julia already has a very nice package for doing mixed models, but the inference, testing hypothesis, confidence intervals there are based on large sample approximations. And yeah, in this talk, you will see if we can do something better for small samples. Because I only have 10 minutes, I will just walk you through a case study to try to convince you that this is worth doing. Particularly, we will be looking at a wind tunnel experiment where we have a car in a wind tunnel and we want to measure the efficiency of the car, the fuel efficiency of this car in various configurations. And we can configure the car in 4 different ways. The first two things you can tweak is the front ride height and the rear ride height. And to do this, you need to shut down the wind tunnel, take the car out of the wind tunnel, disassemble the wheel of the car in the front or the back, put it back together, put the car back in the wind tunnel, and turn the wind tunnel back on. So that's, of course, a lot of work, a lot of effort, costs a lot of money. For this reason, we call these factors hard to change. The other 2 factors, the jaw angle and the grill tape, they're easy to change. The jaw angle is just changing the angle of this platform, and the grill tape is just putting a certain amount of tape here at the front of the car. To do that, you don't need to shut down the wind tunnel. Those are much easier to change. We want to test these factors in 3 different configurations: a low setting, a center setting, a middle setting, and a high setting. And in experimental design, it is often the case that these are encoded as -1, 0, and +1, and then we forget about the engineering units behind them. So you probably know from statistics that it is a good idea to completely randomize your experiment. So yeah, a completely random wind tunnel experiment might look like this, but then you can see here that for the hard to change factors, that they change after every run, which means that after every observation that you gather, you need to shut down the wind tunnel. This costs too much money. The engineers of the wind tunnel don't want to perform this experiment, so it might be a better idea to restrict randomization somewhat. And then we see the experiment over here, and in the statistical jargon, this is called a split plot experiment. And in particular, what we see here is that for the 2 hard to change factors where the wind tunnel has to be shut down to change them, here these keep on having the same value for 5 observations in a row. So the wind tunnel has to be shut down less often. And yeah, this first group of 5 observations is then called the first whole plot. This name whole plot, this comes from agricultural engineering, where these experiments were first used. So plot here is kind of refers to a plot of land. Even though that's not the case in practice in a wind tunnel. So then the engineers of the wind tunnel were okay with performing these experiments, and they gathered the efficiency data. And now we want to model this. We want to make a statistical model of this. However, yeah, when you are doing ordinary least squares analysis, the assumption is that all of your error terms are statistically independent of one another. And when you do such a split plot experiment where you keep the where you do not properly randomize after every run, then it is very dubious that your residuals are really going to be independent. One of the reasons why this might be is because, well, here in the first 5 runs, you use the same configuration for the car. So it might be that you want to put the front ride height to -1, but yeah, your engineers only have a finite amount of precision, so they might put it really to -1.01, and then of course that same error is propagated to all 5 of these observations because you're using the same car, and then your residuals will not be uncorrelated. This is where mixed models comes into the picture. We see here that we want to fit a model with an intercept, some first-order terms, and then some second-order terms, so quite a simple statistical model. But to cope with this fact that we have these blocks in our data set where we did not properly randomize, we allow that the intercept is slightly different for each whole plot. And then on the right-hand side, you see the default inference done by mixed models. And we see here the estimates of the point estimates of all of your terms in the model, some error on that estimates, then some z-score, which measures how far away from zero this effect is, and then a p-value. So a z-score, that's always used in statistics when you have when you do large sample approximations. And then I want to draw your attention here to two particular p-values here, which involves terms only involving the hard-to-change factors. So here you have a p-value e to the minus 10 and a p-value 0.02. If we then move to a mixed model small sample, where we make this adjustment for the inference, we see here that this p-value changed from e to the minus 10 to only 0.002. So that's a huge difference. But you might say, well, okay, that's still a very significant p-value. But if we look here at this other p-value, it used to be 0.02, and now it's 0.08. So depending on what significance level you're testing at, this term now becomes insignificant. Another thing I want to draw your attention here is that for now that we are doing adjustments, we have to calculate a certain amount of degrees of freedom used in a t-test. So statisticians will probably cringe a little bit at my explanation of degrees of freedom here, but think of degrees of freedom as the amount of units of information that are used for a certain estimate. In an ideal case, you want to have a degree of freedom which is on the same order of magnitude as the amount of data that we've gathered. So we have gathered 50 data points. So here for the effects only involving easy to change factors, we have degrees of freedom of 31, which is good enough when you have gathered 50 data points. But when we look at the estimates involving hard to change factors, we see that we only have 4 degrees of freedom. So we are only using, let's say, 4 data points to get to this estimate of the rewrite height, and this degrees of freedom is more on the order of magnitude that you have whole plots in the data set. So, and of course, yeah, in the z-test, you are kind of assuming that you have an infinite amount of degrees of freedom, and 4 degrees of freedom is very far away from an infinite amount of degrees of freedom. So I hope that kind of convinced you that doing these small sample adjustments is worth it in certain experiments. Are these methods used in practice? Yes, they are the recommended method by the FDA for bioequivalence testing. So if you want to test if some generic drug product is equivalent to a brand name drug product, you don't want to do a huge clinical trial again. You just want to do you want to gather a small data set. For this reason, these small sample adjustments are useful there. And in this world of bioequivalence testing, SAS really still reigns supreme. So there are some open source tools like in R you have LMR test, but yeah, I noticed that there was always like 1 or 2% difference in the results between SAS and R. So yeah, I reverse engineered what the difference was between these two methods, and I noticed that yeah, in SAS they were using the observed Fisher information matrix, while in R they were using the expected Fisher information matrix. So the Julia package allows you to choose the hyperparameter such that you can both recover the result from SAS and also from R. In this case study, I showed you how to do t-tests. The package also includes code for f-tests, but I have not yet decided on a clean interface for the user. So look forward to that in the future. Thank you.
Great. We have time for one question while Kieran gets his slides set up. Okay. Let's thank the speaker again.